Okay guys, let's take a look at our lesson for today. This one is on concavity. So the last lesson that we looked at, we talked about intervals of increase, decrease, we talked about relative extrema. This is just another demonstration of how the derivative can give us information about the position function. This is just more information that we can gain from a derivative regarding its position function. The very first thing that we'll look at is the definition, and to be perfectly honest, this definition is very abstract, kind of difficult to get your mind around, so kind of stay with me, because it's abstract because it's actually defining concavity by using the first derivative, which seems kind of, strange. We're using the first derivative to define concavity. Well, right before we talk about that, let's talk, maybe we don't know what concavity is in general, so let's talk about that. This picture over here, we can see that this portion here is concave down. All right, maybe you already know what concavity looks like. It's basically curvature. This is a curvature curved down. Concave down is kind of curvature that's oriented down. Concave up is on this side. This is concave up. It's curvature. The curvature is faced up. Okay, so that's concavity. It's a shape. It's basically a shape. Is it curved down or is it curved up? So that's what concavity is. Now let's go to our definition. So first of all, we are supposed to have a differentiable function, which just means you can take the derivative of it. And we are concave up on an open interval if the first derivative is increasing on the interval. Now, that's kind of hard to really even conceptualize. What does the first derivative look like when it's increasing on an interval? Well, let's go over to the graph right here. So we have this piece is concave up, and let's visualize how can we even see the first derivative off of a position. We think about the slopes of the tangent lines, right? The slopes of the tangent lines. So here at the base, the slope of this tangent line, I don't know, maybe a half, right? So the derivative value there is maybe a half. As we continue up, the slopes are increasing. Right, so that's how we would be able to determine if the derivative is increasing from a picture is looking at the slopes. Again, very abstract, right? We would have to really conceptualize, is the first derivative really increasing there or is it not? Okay, so that's just the definition. Concave down, so we would be concave down on an interval if the first derivative is decreasing on the interval. So what does that look like? Let's think about that. Decreasing. So again, we read from left to right. So let's start here. So that tangent line is pretty steep. I don't know, maybe 10, slope of 10 or something. And the tangent lines are getting less steep. So that means that the first derivative is decreasing. So you see why students usually have trouble with that? It's really abstract. It's talking about the first derivative. I had a question earlier today, well, what about if it's negative? What about if we're looking at, for example, this way? Okay, what does that mean? Is it an absolute value or is it actual value? And it really is an actual value. If we look, so I think you can see this is curved up, right? It's curved up. This is concave up right here. Concave up says that the first derivative is increasing. Okay, so we're basically here, we would be really negative, right? Really negative. And this is less negative. Let's say like negative, I don't know, 100, negative 10, negative. You see how the values of the derivative are getting larger? The values of the derivative are increasing. Are we okay with that definition? Okay. All right, so let's move to the actual test that we use for concavity. The test is much easier to use and work with than the definition. Can you prove something is concave up or concave down with the definition? Absolutely. It's usually not done because it's so abstract. Okay, but can you? Yes, sure you can. You can use that to prove something's concave up or concave down. A more practical technique actually would be to use this test. It's called test for concavity. First, we have to say that y equals f of x is twice differentiable. That basically just means you can take two derivatives of it. That's all. And here's the test. So number one, If the second derivative, okay, we're talking about signs of the second derivative. I'm hoping you're seeing in the future more sign charts, right? We did sign charts in the last lesson on the first derivative. Remember that? Sign charts on the first derivative gave us increase, decrease, relative extrema. Sign charts on the second derivative are going to give us concavity and inflection points. Okay, so lots of sign charts, they mean different things. So if the second derivative is positive on an interval, then the graph of the original function, again, we're using derivatives to describe the original function. Then the original function is concave up. And for me, that's kind of easy to remember, positive up. Well, that's kind of easy, you know, second derivative positive, concave up. If the second derivative is negative on an interval, then the graph of the main function, the position function, is concave down. Again, kind of easy to remember, negative down. Negative's concave down. And that's the test that we're going to be using with sign analysis. Okay? This concept right here, at first, may be kind of difficult to kind of wrap your mind around. And so I have it written out here specifically that straight lines don't have concavity. Let's think about it for a second. So concavity is a measurement of curvature. It's curved, right? Lines don't have curves. Lines don't have any curves. So first, that's like, okay, well, how could it have concavity? And then the second thing is, lines don't really have a second derivative, right? The first derivative of a line would be a constant. The second derivative would be nothing. Right? Nothing. So they don't really have a second derivative. So that kind of makes sense. Straight lines do not have concavity. So I just want to point that out. The last concept we'll be looking at today is points of inflection. A point of inflection is basically where the concavity changes. So as we're looking at our sign charts, the critical numbers from the second derivative can yield inflection points. Okay? Questions about the concept so far? We have a couple of examples to do. Yeah, on this particular graph right here, the point of inflection would be right at 0, 0. Yeah, that's where we changed. So we went from concave down to concave up at 0, 0. So that would be the point of inflection there. Okay, anything else? Okay, we have a couple of examples on the next page to look at. Okay, so the first one basically says use the first and second derivatives of that function to determine intervals on which f is increasing, decreasing, concave up, concave down, and locate all inflection points. And then we're going to confirm our results with a graph on our calculator. All right, so let's start. So we're going to find the first derivative. So f prime of x is 3x squared minus 6x. Okay, so what do we do to find intervals of increase, decrease? That was our last lesson. Remember, we're looking for critical numbers. So I set the first derivative equal to 0. So 0 equals 3x squared minus 6x. And then I factor. So I have a critical number at 0 and a critical number at 2. Do I have, and the kinds of critical numbers those are stationary points. Right? Do I have any singular points on that derivative of 3x squared minus 6x? Is it undefined anywhere? No, it's a polynomial, right? Don't you wish everything was a polynomial? Wouldn't that be nice? They're so, you know, they're so easy. So, all right, so we have 0 and 2. Since we're going to have multiple sign charts, we really need to keep in our mind what we talked about in the last lesson is where do we go to test the signs on the sign chart? We go back to where we got the numbers from, right? Back to where we got the numbers from. So where did we get 0 and 2? We got them from the first derivative. So I'm going to test my signs in the first derivative. So when I do that, I get plus minus plus. And now we can analyze what's going on here. So for our increase, decrease. So we have an interval of increase at negative infinity to 0 and 2 to infinity because f prime is greater than 0. Remember our justification, just a few seconds. We're decreasing from 0 to 2 because f prime is less than 0. Okay, that's just a recap from the previous lesson. Are we okay with that? Okay. So now let's work on concavity. So we need to take the derivative of the first derivative. So the second derivative is 6x minus 6. We need critical numbers off of it, so we set it equal to 0. 0 equals 6x minus 6. And we get x equals 1. That is a stationary point. Does this derivative, this second derivative, have any singular points? No, right? It's a polynomial. It doesn't have singular points. So let's do our sign chart. We just have one number on it, and I'm just noting it because this was the first derivative sign chart. This is the second derivative sign chart. And again, where did I get this number from? I got it from the second derivative, so that's where I go back and test my signs in the second derivative. And when I do that, I get negative and positive. All right, so let's interpret what that means. What does that mean about the original function? Well, that means that from negative infinity to 1, we are concave down. Because f double prime is less than 0. All right, and from 1 to infinity, we are concave up because f double prime is greater than 0. Okay so far? The last question is, do we have an inflection point, or locate all the inflection points? Now the inflection points are where the second derivative changes signs, or where we change concavity. Did this particular graph, or is it going to change concavity? Yes, it changes concavity at 1, so therefore we have an inflection point at 1. So we have an inflection point at 1. Now how do I get the y value? Here we get a little mixed up sometimes. So all of this information is describing the behavior of f. That's what it's all about. It's all about f, right? It's all about the function, the original position function. So if I want to locate a value of an inflection point or a relative max or min, where do I go to get the value? I go back to the original function, f, right? Because it's all about that one anyway. So I'm going to take this 1 and I'm going to put it back up here into the original function to find the y value, and that ends up being negative 1. And so the justification here is because f double prime changes signs. Okay, so I didn't say which way the signs went, did I? I didn't say changed from negative to positive. Could I? Sure. Do I need to? Does it matter with concavity? Does it matter which way the signs go? It just matters that they change. Okay, that's not the same for relative extrema, right? We have to say change from positive to negative or from negative to positive for relative extrema. Otherwise, we wouldn't know if it did, right? So if you're worried that you might forget to put the change signs on the other one, just go ahead and say changes from negative to positive at x equals 1. Okay, or you can just say changes signs at x equals 1, whichever you like. Is that okay so far? So what we're going to do is we're going to take, I'm going to have to erase this and pull up my calculator. We're going to take this information, our increase, decrease, our concavity, and we're just going to look at the graph and see what's going on with the graph. Okay, so I'm going to graph that. Okay, so let's pull, I think I already have it in my calculator. Yeah, actually I already have it graphed. So I just put it in my y1. Here's the equation. The original, this is the function equation, right? Not any of the derivatives, the original. And so we look at the graph. And what did our information say? Let's see. It said we were increasing from negative infinity to 0. Okay. Yeah, that's true, right? Increasing from negative infinity to 0. Then we were decreasing from 0 to 2. Okay, that's verified. Then we were increasing from 2 to infinity. Okay, so that all checks out. We were talking about concavity. We are concave, let's see, we are concave down from negative infinity to 0. excuse me, to 1, negative infinity to 1. So right here. So I hope you can see this portion right here is concave down. You can visually see that that's concave down. And the concavity changes at that exact point, at 1, negative 1. And then we change to concave up from 1 to infinity. Okay, we okay with that? Okay. All right, let's take a look at our very last example. So now we have, this is a graph of f, and we are asked to state the signs of f prime and f double prime on the interval from 0 to 3. Okay, so we're reading a graph of f. How do we find the first derivative off of a graph of f? We look at the slopes of the tangent lines, right? All these slopes are negative, so f prime is less than 0 on 0 to 3. Okay, so this is a position. How do we read concavity off of position? We look at its curvature, right? So this is concave up, it's curved up, so therefore our second derivative has to be positive. So f double prime has to be greater than 0 on 0 to 3. Now I want to give you a caution, because you also will have to interpret things using a graph of the first derivative. Okay, so let's just practice that just real quick. I want to practice using the graph. Let's pretend that this is first derivative. Okay, that's the first derivative. How would I look at concavity off of the first derivative? Okay, so the sign of the first derivative, that's all positive. So f prime would be greater than 0 if this were the first derivative. Okay? The second derivative, if this were a graph of the first derivative, what would I do? Well, the second derivative is the derivative of the first derivative, right? So I would look at slopes of tangent lines on the first derivative to get the sign of the second derivative. So I'm looking at slopes. All these slopes are negative, so the second derivative would be less than 0. So notice those are completely different answers. So you really have to pay attention to what kind of graph you are looking at as you interpret. So we're going to be doing a lot of this. Okay, pay attention to what kind of graph you're looking at as you interpret these questions that you'll be asked. Okay? Anything else? Is that it? All right, great.